Module 6, Lecture B, Time Series Features. By the end of this lecture, you will be able to represent civil engineering time series data using pandas and NumPy structures, extract temporal features such as lag values, rolling averages, and rate of change, and evaluate simple time series baselines and visualize prediction errors. Temporal data. Time indexing. Time indexing links each data point to a specific moment, keeping measurements in the correct order and context. In civil engineering, this helps show how infrastructure conditions change over time, such as bridge strain, pavement temperature, or traffic patterns. Using time as an index makes it easier to align, sort, and filter data for meaningful analysis of temporal trends. A well-built time index helps analysts manage both regular and irregular time series data. It shows whether measurements are evenly spaced, reveals missing time periods, and makes it easier to combine sources collected at different frequencies. In civil engineering, this lets data such as sensor readings, weather records, and inspection or crash reports be organized in a shared time context while preserving their original timing and precision. Accurate time indexing is essential in civil engineering data analysis because time zones, daylight saving changes, reporting delays, and timestamp precision can affect results. If these details are ignored, patterns and performance measures may be misread. Tools like Pandas and NumPy help organize time data so it can be sliced by project phase, grouped by period, and resampled to extract useful features about infrastructure behavior. Python code. Time indexing. Time indexes help organize engineering measurements by linking data to meaningful timestamps. In Pandas, these timestamps can serve as indexes, making it easier to see temporal patterns even in small examples. We begin by importing 3 core libraries for time series analysis. NumPy supports efficient numerical calculations. Pandas helps organize and analyze time index data, and Matplotlib provides tools for plotting and visualizing results. Together, they form a practical toolkit for working with engineering measurements over time. We create an hourly time index for bridge monitoring using Pandas. The sequence starts at 6 in the morning on March 1st, 2026, and includes 8 timestamps spaced 1 hour apart. This provides precise time labels for analyzing measurements that change over time, such as bridge strain. Strain readings, which measure bridge deformation, are first stored as numerical values in a NumPy array. They are then organized in a Pandas data frame with a column for strain and microstrain. Hourly timestamps are used as the index, so each reading is linked to a specific time for time-based analysis. Naming the data frame index as measurement time makes its meaning clear. It shows that the index values are the times when each strain measurement was taken, which makes the data easier to read and interpret. We filter the Pandas data to a specific time window, 8 to 10 in the morning on March 1st, 2026. This keeps only the rush hour measurements, so the strain readings can be analyzed for that busy period. To check whether timestamps are evenly spaced, compare the time gaps between each consecutive timestamp. After removing any missing gap values, count how many distinct gaps remain. If there is only one unique gap, the timestamps are regularly spaced. This step summarizes the bridge measurement data by checking its time range, spacing, and size. It reports the first and last timestamps, verifies whether the measurements are evenly spaced, calculates the average rush hour strain rounded to 1 decimal place, and prints the data frame dimensions. The strain data is plotted from the data frame with strain and microstrain on the y-axis. Circular markers make each data point easier to see, and the legend is removed because the plot is simple. A compact figure size is used for quick visual analysis. The plot is prepared by giving it a clear title and labeling the axes so the time of each measurement and the strain values in microstrain are easy to understand. The layout is adjusted to prevent labels from overlapping, and the plot is then displayed to show how bridge strain readings change over time. This example shows how pandas can use time indexing to analyze bridge strain readings. Hourly measurements are assigned timestamps starting at 6 in the morning on March 1, 2026. Then a rush hour period from 8 to 10 is selected to compute the average strain. The script also checks the time range, data shape, and regular hourly spacing, then plots strain over time to show how the readings change. Time indexing. Time indexing connects each data point to a specific moment, so the order and timing of measurements are clear. In civil engineering, this is essential because data such as bridge strain or traffic counts only becomes meaningful when tied to time. Pandas stores this timing as a time index for calendar-based analysis, while NumPy handles the numerical values efficiently. A good time index shows whether data is collected at regular or irregular intervals and makes time-based analysis possible. In Pandas, it lets you select specific dates, compare periods, and align measurements from different sources. This is especially important in civil engineering, where data such as rainfall and structural health readings must be connected over time to understand system behavior. Time indexing is essential for reliable civil engineering time series analysis. A clear time index helps detect missing or duplicate timestamps, unexpected gaps, and issues caused by time zones or daylight saving changes. This supports accurate feature extraction and helps analysts interpret system performance during specific events. Python code time indexing. Civil sensor data is organized by time indexes, linking each observation to when it was recorded. Pandas pairs timestamps with measured values, while NumPy stores the measurements efficiently as compact numeric arrays. The script begins by importing NumPy for efficient numerical work and Pandas for managing and analyzing time series data. These libraries provide the foundation for later operations with arrays and time-indexed data. Use the Pandas date range feature to create 6 hourly timestamps starting at midnight on March 1, 2026. Setting the frequency to hourly keeps each timestamp 1 hour apart, which helps align time-based data, such as sensor readings, to precise intervals. Strain readings are stored in a NumPy array to handle numerical data efficiently. The array holds 6 strain measurements using floating point values to support precise calculations and later numerical analysis. The code verifies that the number of timestamps matches the number of strain readings, so each time point has a corresponding value. If the counts differ, it stops execution with an error, helping catch data alignment problems before analysis continues. We organize the strain readings as a Pandas series indexed by time. The values come from the NumPy array, and the generated timestamps link each reading to its measurement time. The series is given a clear descriptive name to show that it represents bridge strain in microstrain. We filter the strain series to keep only readings from the morning window between 2 and 4 a.m. on March 1, 2026. Using the Pandas location method, this selects just the data points in that time range so they can be analyzed separately. We create an irregular inspection log by converting date and time strings into Pandas timestamps. This lets Pandas recognize each inspection time correctly, which is needed for later time-based indexing and analysis. Pavement rut depths are stored as 3 floating point values in a NumPy array. This makes the measurements easy to manage and efficient to use for later numerical analysis. A Pandas data frame is created to organize rut depth inspection data measured in inches. The rut depth values come from a NumPy array, and the data frame uses the inspection timestamps as its date-time index. This makes it easy to analyze and retrieve rut depth measurements by inspection time. To check how evenly bridge sensor readings are spaced, convert the strain series index into a Pandas series, and calculate the differences between consecutive timestamps. After removing missing values, the remaining time gaps show how regular the sensor reading intervals are. This section checks how the bridge strain and inspection data are organized in time. It verifies the strain series index type and starting timestamp, reviews the morning strain readings, and confirms that the strain measurements are evenly spaced by hour. It also checks that inspection times are irregular and reports the total number of inspection records. This script shows how Pandas and NumPy handle time index data. It pairs hourly bridge strain measurements with matching timestamps, builds a Pandas series, and selects readings from a specific morning time window. It also creates a separate dataset for rut depth measurements taken at irregular inspection times. The output confirms that the sensor readings are evenly spaced, the inspection times are irregular, and reports key index and entry details. Wide time series. A wide time series stores each time point as a row and each measured variable as a column. In civil engineering, this is useful for monitoring infrastructure with many sensors at once, such as bridge or water system measurements. By placing readings side by side for the same timestamp, the format makes it easy to compare and align simultaneous sensor data. Wide time series data fits naturally in Pandas and NumPy because both handle synchronized measurements well. In Pandas, time forms the index, and each signal becomes a column, making it easy to select time ranges, compare sensors, and plot results. In NumPy, the same data becomes a two-dimensional array with observations in rows and features in columns, which matches the format expected by many clustering and machine learning algorithms. Wide time series are useful, but they require careful timestamp alignment, especially when sensors record at different intervals. Gaps from sensor failures or communication problems can reveal data quality issues. When handled well, this format helps engineers compare variables, such as bridge strain and temperature, and supports later feature extraction and prediction. Python code, wide time series. Wide tables organize sensor data by aligning readings to timestamps. In Pandas, time is typically stored as the index, while NumPy treats rows as individual observations. We import 3 core libraries for data work: NumPy for numerical operations and arrays, Pandas for manipulating structured data, and Matplotlib/pyplot for creating visualizations. Together, they provide a basic toolkit for data analysis and plotting. Create an hourly sequence of 6 timestamps using Pandas, starting at midnight on January 1st, 2026. Each timestamp is 1 hour apart, providing a time index for aligning sensor data collected at those moments. A dictionary is used to store synchronized bridge sensor data, with each key representing one measurement type. It includes strain readings for girders A and B, deck temperature, and wind speed. Each measurement list has 6 values from the same timestamps, keeping the data aligned for analysis. We create a Pandas data frame from the sensor data and align it with the generated timestamps, so each row represents readings at a specific time. Naming the index timestamp makes the table clearer and shows that the observations are time-based. We first set the expected data frame size to 6 rows and 4 columns, matching the anticipated timestamps and sensor readings. An assertion then checks whether the actual data frame has that shape. If it does not, an error is raised, helping catch data structure problems before analysis continues. We convert the data frame to a NumPy array with floating point values, so it is ready for efficient numerical work. Then we check that the array has the expected shape, confirming that the data structure was preserved during conversion. We quickly inspect the time series data by checking the table's size, sensor columns, and first timestamp. We then confirm that the NumPy array has the same dimensions as the data frame, and preview the first row of sensor readings rounded to 2 decimal places. The sensor data is plotted over time using a Pandas data frame, focusing on strain measurements from girders A and B. A line plot with markers shows how the strain changes at each recorded point, and the figure size is chosen to keep the chart clear and readable. The plot is formatted to clearly show bridge strain sensor data over time. Its title identifies the wide time series. The horizontal axis is labeled as timestamp, and the vertical axis is labeled as microstrain. A lightly transparent grid is added to make the data easier to read and compare. Use Matplotlib's tight layout function to adjust spacing so plot elements do not overlap. Then use the show function to display the plot, making it possible to inspect the time series trends and relationships visually. This script builds a small, hourly time series dataset of bridge sensor readings using Pandas, including strain from 2 girders, deck temperature, and wind speed. It verifies the data frame structure, converts the data to a NumPy array, and prints key summary information such as dimensions, column names, and the first timestamp. It then plots the 2 girder strain readings over time, making it easy to compare how strain changes across the 6-hour period. Temporal feature extraction. Lag feature basics. Lag features help predictive models use time series data by including past measurements as inputs. This is important in civil engineering because many systems depend on earlier conditions, such as traffic volumes, structural vibrations, or water levels after rainfall. By adding these past values, models can better capture temporal patterns and relationships. Lag features help models capture how past values influence current or future behavior. They represent persistence, delayed effects, and recurring patterns, such as gradual changes, later responses to events, or regular peaks. The best lag intervals depend on how often the data is collected and how the system behaves. Lag features must respect time order, so a model should only use information available before the prediction point, and never future data. They can introduce missing values at the start of a dataset, and using too many similar past values may add redundancy, especially when measurements change slowly. Choose lags that reflect meaningful delays and system memory, guided by engineering knowledge and exploratory analysis. Python code. Lag feature basics. Lag features capture recent system history, which is often important for civil sensor data. In this example, they are used with bridge traffic counts. We import NumPy for efficient numerical calculations, Pandas for working with and analyzing data, and Matplotlib's plotting tools for visualization. Together, these libraries prepare the script to handle arrays, manage data, and create charts. We create an hourly time index with Pandas, starting at 6 in the morning on January 1st, 2026. It contains 24 timestamps, one for each hour, so traffic data can be aligned to specific times of day. This code creates a NumPy array of hourly traffic counts for a full day. The values model a realistic pattern, with lighter traffic overnight and heavier traffic during peak hours. This dataset is then used to analyze traffic trends and prepare lag features later in the script. We create a Pandas data frame to organize the traffic observations over time. It stores the traffic counts in one column and uses the hours as the index, making the data easier to analyze as a time series. Lag features are created by adding columns that show past traffic counts, such as values from 1 hour, 3 hours, and 6 hours earlier. These shifted values let the model compare current traffic with recent history, helping reveal how earlier conditions may influence the present. Rows without earlier observations are removed using the drop missing values method. Then the clean data is copied, so later changes do not affect the original. An assertion then checks that the feature table is not empty, confirming that lagged features were created and enough data remains. If the table is empty, an error signals a problem in the processing step. The output explains that lag features come from earlier traffic counts, then shows a quick preview of the feature table. It displays the first 4 rows, rounds the values to remove decimals, and formats the result as clean text so the data is easier to read and interpret. We measure how current traffic counts relate to traffic from 1 hour earlier by calculating their correlation. This produces a single value showing how strongly present traffic depends on its recent past. The code reports how strongly current traffic counts relate to counts from 1 hour earlier, showing the correlation rounded to 2 decimal places. This gives a quick sense of how useful the previous hour is for predicting current traffic. It also notes that early rows without enough past data were removed, so the analysis uses only complete records. Create a clear plot of traffic counts over time. Then add a second series showing the counts from 1 hour earlier. Use different markers for the current and lagged values so they can be compared easily. This helps reveal patterns or correlations between present traffic and its 1 hour lag. The plot is labeled to make the traffic comparison easy to understand. Its title identifies the bridge traffic data and the 1 hour lag feature, while the axes show time and vehicles per hour. A legend distinguishes the current traffic values from the 1 hour lagged values. The code improves the plot's readability by rotating the time labels and tightening the layout so everything fits cleanly. It then displays the chart, making it easier to compare current traffic counts with values from 1 hour earlier. This script shows how to create lag features for hourly bridge traffic data by using past traffic counts from 1, 3, and 6 hours earlier. It removes rows that do not have enough history, then measures how strongly the current count relates to the 1 hour lag. A comparison plot helps show how lagged values follow traffic patterns over time. This is a common time series technique for using past behavior to support future prediction. Rolling averages. Rolling averages smooth noisy time series data by reducing short-term fluctuations, making important patterns easier to see. In civil engineering sensor data, such as bridge vibration or water level readings, this helps engineers focus on meaningful trends and shifts instead of reacting to every small variation. Choosing a rolling average window is a trade-off between speed and smoothness. A short window responds quickly to changes but leaves more variability, while a longer window reduces fluctuations but can lag behind real shifts. The best choice depends on how the system behaves and what decisions the data needs to support. Rolling averages summarize recent trends, making data easier to interpret and more useful for prediction, anomaly detection, and visual checks. They can help forecast future conditions and highlight unusual changes when compared with raw data. To avoid misleading results, rolling averages must be calculated using only past data. When implemented correctly, they strengthen both model performance and analysis. Python code, rolling averages. Rolling averages help smooth noisy engineering measurements, with the window size balancing responsiveness against smoothness. Pandas makes it straightforward to extract these kinds of time-based features. We begin by importing the key libraries needed for the analysis. NumPy supports efficient numerical calculations. Pandas helps organize and manipulate tabular time series data. And Matplotlib is used to create plots for visualizing the data and rolling averages. The setup makes the simulated sensor data reproducible, then creates 48 hourly timestamps starting on January 1st, 2026. It also adds a simple linear trend that rises from 2 to 3.2, representing a gradual increase in readings over 2 days. The simulated water level data combines 3 parts: an underlying trend, a daily sine wave pattern, and small random noise. The sine wave adds a natural 24-hour cycle across the 48-hour series, while the noise adds minor variation. Together, these elements create more realistic sensor measurements with both periodic behavior and randomness. The water level measurements are stored in a Pandas data frame, with the hourly time series used as the index so that data can be analyzed over time. A check is then added to confirm there are at least 6 observations, since operations such as rolling averages need enough data points to be meaningful. Rolling averages help smooth water level data and reveal trends. A 3-hour rolling average reduces short-term fluctuations, while a 12-hour rolling average smooths the data further to show longer-term patterns. Both are created by applying a rolling window and calculating the mean for each window. The analysis first reports the total number of hourly water level readings, then compares variability in the raw measurements with smoothed versions. It calculates the standard deviation of the raw data, the 3-hour rolling average, and the 12-hour rolling average, each rounded for clarity to show how smoothing reduces variation. Finally, it compares the most recent raw water level with the latest 12-hour rolling average to highlight the longer-term smoothing effect. Create a clear plot of water level readings over time, showing the raw sensor data alongside 3-hour and 12-hour rolling averages. The raw data is drawn more lightly, while the rolling averages use thicker lines, so the smooth trends are easier to compare. This makes it clear how longer averaging windows reduce short-term variation and reveal broader patterns. The plot is labeled to make the water level monitoring data easy to understand. Its title identifies the focus on rolling averages, the horizontal axis shows time, and the vertical axis shows water level in meters. A legend is added so viewers can distinguish the raw measurements from the rolling averages. To make the plot easier to read, a lightly transparent grid is added so the data and lines are easier to distinguish. A tight layout then keeps labels and titles from overlapping or being cut off. Finally, the plot is displayed for visual analysis of the water levels and their rolling averages. This script creates 2 days of simulated water level readings with a trend, daily cycle, and random noise. It then uses rolling averages over 3 and 12 hours to smooth the data and reveal patterns at different timescales. The output summarizes the readings and compares raw and smoothed variation, while the plot shows that the shorter average keeps more short-term changes and the longer average highlights broader trends. Rolling averages. Rolling averages help make noisy time series data easier to interpret by smoothing short-term fluctuations. In civil engineering, this can reduce the effect of sensor noise or brief environmental changes, such as spikes from heavy vehicles on a bridge. By focusing on recent observations, rolling averages make broader trends, like gradual strain increases or temperature shifts, easier to identify. A rolling average updates over time using a fixed span of recent data. The window length controls the trade-off. Shorter windows respond quickly but can include more noise, while longer windows smooth the trend but may react more slowly to real changes. In practice, rolling averages help summarize recent conditions, such as rainfall patterns or pavement temperature, while balancing responsiveness and smoothness. Rolling averages help separate brief anomalies from real trends in time-based data. By smoothing short-term fluctuations, they can reveal whether values are steadily rising, falling, or staying stable, such as in sensor readings or construction productivity. In predictive models, they reduce noise and add useful context, but they must be built without using future data so the model reflects real-world timing accurately. Python code, rolling averages. Rolling averages help smooth noisy civil sensor data by summarizing recent readings over short time windows. To keep the analysis valid, the window must be shifted carefully so it does not use future data. We import 3 core Python libraries for data work: NumPy for efficient numerical operations, Pandas for manipulating structured data, and Matplotlib PyPlot for creating visualizations. Together, they provide a strong foundation for data analysis and presentation. We create a reproducible set of hourly bridge strain measurements by fixing the random seed, then generating 48 hourly timestamps, starting on January 1st, 2026. A steady linear trend from 100 to 112 is combined with normally distributed random noise to mimic realistic variation in the data. We create a strain data series with a steady trend plus random noise to mimic normal sensor variation. Then we add a short spike between hours 24 and 28, representing a temporary increase, such as heavier bridge traffic. This artificial peak helps test whether rolling averages can detect sudden changes in the data. A Pandas data frame is created to store the strain measurements, with each value linked to an hourly time index. The strain data is placed in a single column, and the time index ensures each measurement matches a specific hour. An assertion then checks that the data frame has 48 entries, confirming the data is complete and properly aligned. We calculate rolling averages for the strain data using only past readings. A 3-hour average captures short-term changes, while a 12-hour average shows longer-term trends. These averages smooth the data without relying on future observations. To avoid data leakage in rolling average features, shift each rolling average back by one time step before using it for prediction. This is done for both the 3-hour and 12-hour averages, so each value is based only on information available up to that point. As a result, the model does not accidentally use future data. The code first reports the number of hourly bridge strain readings to show the dataset size. It then compares rolling averages, where shorter windows respond faster to changes and longer windows give smoother trends. To avoid using future information, the rolling features are shifted back by 1 hour. Finally, it shows the most recent rows with the original readings and shifted rolling averages, rounded for easier review. The plot compares raw strain measurements over time with two smoothed trends. The raw data is shown with partial transparency, while safely shifted 3-hour and 12-hour rolling averages are added to avoid future data leakage. Together, these lines make it easier to see both short-term and longer-term patterns in the strain data. The plot is formatted to clearly show rolling averages for bridge strain monitoring. Its title gives the visualization context. The horizontal axis is labeled as time, and the vertical axis shows strain and microstrain. A legend is added so listeners or viewers can distinguish the raw strain data from the rolling average lines. The code uses Matplotlib's tight layout function to automatically adjust spacing, so labels and titles do not overlap. It then calls the show function to display the bridge strain data and its rolling averages on the screen. This script simulates 2 days of hourly bridge strain readings, with a trend, noise, and a temporary traffic-related spike. It stores the data, then computes 3-hour and 12-hour rolling averages using only past readings, shifted so they are safe for prediction without future leakage. The short average responds faster to changes, while the longer average gives a smoother trend. The final output summarizes recent readings and plots the raw data with both rolling averages to show their smoothing behavior. Forecast baselines. Naive forecasts. A naive forecast is a simple time series baseline that predicts the next value will be the same as the most recent one. In civil engineering, this might mean assuming a bridge sensor reading or traffic count stays unchanged in the near future. Its main value is as a benchmark. More advanced forecasting models should be used only if they consistently perform better than this basic assumption. Naive forecasts are useful when a time series changes slowly, so the most recent value is a reasonable short-term prediction. They can work well for minute-by-minute sensor data, but may fail when patterns shift, such as in daily traffic or electricity demand during extreme conditions. For data with regular cycles, a seasonal naive forecast, using a comparable past period, like the same hour yesterday, is often more appropriate. A naive forecast provides a simple benchmark for judging time series models. If a model cannot beat it, the model may not be learning patterns beyond basic trends. Naive forecasts often work well in stable periods, but lag during sudden changes. So comparing against them helps show when simple assumptions are enough and when more advanced modeling is needed. Python code. Naive forecasts. A naive forecast simply uses the most recent observed value as the next prediction. This can work reasonably well for civil sensor data, because readings often persist over short periods. Such baselines help show whether more complex models provide real added value. We import 3 key Python libraries for the analysis. NumPy supports efficient numerical operations. Pandas helps organize and manipulate data in structured tables. And Matplotlib's plotting tools let us visualize the data and forecasts. We set up a reproducible simulation by using a random number generator with a fixed seed of 42. The simulation covers 48 hourly periods, starting on January 1st, 2026. These hourly timestamps provide the time structure for building a deterministic traffic pattern with controlled randomness. A daily traffic pattern is modeled with a sine wave centered around 120 vehicles and varying by about 35 vehicles. Random noise, with an average of 0 and a standard deviation of 8, is added to reflect real-world variation. The combined values are rounded to whole numbers to represent vehicle counts. The traffic data is organized in a Pandas data frame, with vehicle counts indexed by hour. A naive forecast is then created by using the previous hour's traffic count as the prediction for the current hour. The forecast error is found by comparing each actual count with its naive prediction, giving a simple measure of prediction accuracy. The data is cleaned by removing rows with missing values and copying the result so the original data stays unchanged. Assertions then confirm that the clean data has the expected length, accounting for the first row without a forecast, and that the naive forecast column contains no missing entries. These checks ensure the dataset is complete and ready for further analysis. Forecast accuracy can be summarized with 3 key measures. Mean absolute error averages the size of the errors. Root mean squared error gives extra weight to larger errors. And the final error value shows how the most recent forecast performed. The code evaluates a naive traffic forecast that predicts each hour's count using the previous hour's count. It reports how many hourly observations were tested, then summarizes accuracy with mean absolute error and root mean squared error, with the latter emphasizing larger mistakes. It also shows the most recent forecast error to indicate how well the latest prediction performed. We create a matplotlib plot to compare actual traffic counts with a naive forecast. The actual vehicle data is drawn as a solid line, while the forecast is added on the same axis as a dashed line. Using the same time index for both lines makes it easy to visually judge how closely the naive forecast follows the real traffic pattern. The plot uses vertical gray lines to show the error between each actual traffic value and its naive forecast. It also adds a clear title, labels the y-axis as vehicles per hour, and includes a legend, so viewers can distinguish the actual values from the forecasts. To make the plot easier to read, the x-axis dates are automatically formatted and the layout is tightened to prevent overlapping elements. The plot is then displayed so the data, forecasts, and errors can be viewed together, making it easier to assess the naive forecast's performance. This script shows a simple baseline for forecasting hourly traffic. It creates synthetic traffic data with a repeating daily pattern and random variation, then predicts each hour by using the previous hour's traffic count. It evaluates the forecast with mean absolute error and root mean squared error, and compares the actual and predicted values in a plot. The result helps show how a naive forecast performs before trying more advanced models. Residual visualization. Residual visualization shows how actual values differ from a simple baseline forecast, such as assuming the next time series value matches the last one or follows a weekly pattern. These residuals reveal where the forecast is wrong and help judge whether more complex models are worthwhile. Plotting residuals over time makes it easier to see when and why predictions fail, rather than relying only on a single error score. A residual plot shows forecast error over time, and ideally the error should stay centered without clear trends or repeating patterns. If a pattern appears, it suggests the baseline model missed important information. In civil engineering, this can reveal effects from operations or environmental changes, such as pavement temperature errors rising during a heat wave because the baseline responds too slowly. Residual visualization helps analysts tell whether forecast errors are random noise or signs of a deeper problem. A single large error may point to a temporary disruption or faulty sensor, while repeated patterns suggest the model is missing an important feature. By examining residuals, Analysts can decide whether to improve the model, check the data, or investigate real changes in the system. Python code, residual visualization. Residual plots can reveal errors in baseline forecasts, especially because civil time series often include recurring rhythms. Simple visual checks help engineers diagnose these patterns and improve their understanding of forecast performance. We import 3 core Python libraries for data work: NumPy for efficient numerical operations and arrays, Pandas for manipulating structured data, and Matplotlib's plotting tools for creating visualizations. Together, they provide the basic foundation for analyzing data, performing calculations, and presenting results visually. The setup makes the simulated traffic data reproducible by fixing the random number generation. It then defines 72 hourly intervals, representing 3 days, and creates a sequence of hourly timestamps starting on January 1st, 2026. These timestamps become the time index for the traffic data. To model daily traffic with realistic variation, create hourly time points, then combine 3 components: a sine-based daily cycle, a gradual upward trend, and random noise. The sine wave captures repeating daily traffic patterns, the trend represents steady growth over time, and the normally distributed noise adds real-world unpredictability. Observed traffic counts are created by combining a base level with a daily pattern, a trend, and random noise to make the data more realistic. The counts are then stored in a Pandas data table with an hourly time index and a vehicles per hour column, making the traffic data easy to analyze over time. A naive 1-hour traffic forecast uses the previous hour's vehicle count as the prediction for the current hour. The forecast error is then found by comparing this prediction with the actual observed count. These differences, called residuals, show how far the simple baseline forecast was from reality each hour. Rows with missing values are removed, so each remaining record has both an observed value and a forecast value for comparison. In this case, only the first row is dropped because it lacks a forecast. A copy of the clean data is then used for analysis, and a check confirms that the dataset is exactly 1 row shorter than the total number of periods. Forecast accuracy can be summarized with 3 residual-based measures. Mean absolute error shows the typical error size regardless of direction. Bias shows whether forecasts tend to be too high or too low, and root mean squared error gives extra weight to larger mistakes. We summarize the diagnostic results by reporting how many valid hourly observations were evaluated, then showing key error measures for the naive traffic forecast. The mean absolute error gives the average residual size in vehicles per hour. The average residual bias shows whether forecasts tend to be too high or too low, and the root mean squared error reflects overall residual variability. Together, these metrics provide a quick view of forecast accuracy and bias. Create a Matplotlib plot with a chosen size, then show the forecast residuals over time as connected points. Add a horizontal 0 line as a reference, so it is easy to see when residuals are positive or negative. This visual check helps diagnose forecast accuracy by revealing deviations and possible patterns. The plot is formatted to show residuals from a naive traffic forecast. Its title explains the purpose. The horizontal axis represents time, and the vertical axis shows observed values minus forecast values. A lightly transparent grid is added to make the data easier to read against the axes. To finish the visualization, the code formats the date labels so they are readable, adjusts the layout so plot elements fit cleanly, and then displays the plot. These final steps make the residual plot for the naive traffic forecast clearer and easier to interpret. This script creates 3 days of hourly traffic data with a daily pattern, a trend, and random noise. It makes a simple 1 hour ahead forecast by using the previous observation, then compares the forecast with the actual values. The residuals are summarized with error measures such as mean absolute error, bias, and root mean squared error. A residual plot helps show when the forecast is most inaccurate and reveals patterns in the errors. Error visualization. Error visualization turns forecast errors into patterns that are easier to interpret. Instead of relying on one error value, plotting errors over time shows whether a model's mistakes are isolated, repeated, or tied to specific events. In civil engineering, this matters because an error's timing can be as important as its size, especially during peak loads or adverse conditions. Plot predicted and observed values on the same timeline to spot where the model goes wrong. Consistently high predictions suggest overprediction, while consistently low ones suggest underprediction. These visual patterns can reveal bias, missed cycles, or systematic failures that a single accuracy score may hide. Error visualization shows where a baseline forecast works and where it breaks down. Patterns such as errors increasing during unusual loads, storms, or schedule changes can reveal missing factors in the model. This helps engineers and decision-makers understand the limits of a simple forecast and use it as a fair benchmark for more advanced models. Python code error visualization. Use synthetic civil time series data to clearly show baseline forecast errors by comparing predicted values with the observed results. We begin by importing 3 key libraries for data analysis and visualization. NumPy supports efficient numerical work. Pandas helps organize and manipulate structured data, such as time series, and Matplotlib PyPlot is used to create plots and graphs for understanding and presenting results. A fixed random seed is used so the simulation produces the same random values each time, making the example reliable for testing and demonstration. The time series is then set to cover 60 time points, such as 60 days. We create a daily timeline for monitoring bridge strain using a Pandas date range. It starts on January 1st, 2025, and spans 60 days, with one date for each day. This time index helps align strain observations and forecasts over the monitoring period. To simulate observed strain in microstrain units, the data combines a slow upward trend with a repeating weekly pattern. The trend rises gradually from 100 to 112 over the full time period. A sine-based cycle is then added and scaled to create regular fluctuations, representing natural weekly variation in strain. Random noise is generated from a normal distribution with mean 0 and standard deviation 1.8 to represent real-world variability. This noise is added to the trend and cycle components to create the observed strain, combining predictable patterns with random fluctuations. We add 2 artificial anomalies to the observed strain data to test the forecasting model. One point is increased to create a sudden spike, and another is decreased to create a sudden drop. These changes simulate irregular loading events and help evaluate how robust the model is under unexpected conditions. A Pandas data frame is used to organize the simulated strain time series. It stores the observed microstrain values and uses the monitoring dates as the index, so each measurement is aligned with its corresponding day. This makes the data easier to manage and analyze over time. A naive persistence baseline forecast uses yesterday's observed microstrain value as today's prediction. After shifting the observations forward by one time step, Any missing values created by the shift are removed, so the data is clean for analysis. Forecast error is found by comparing observed microstrain with the forecasted value. The signed error shows direction. Positive means the forecast was too low, while negative means it was too high. Taking the absolute value gives the error size regardless of direction, which helps judge overall forecast accuracy. This check confirms that the observed and forecasted microstring data have the same number of values. If the lengths differ, the program raises an error to signal misaligned data. This helps ensure the error analysis is accurate. Mean absolute error shows the typical size of forecast errors by averaging their absolute values, ignoring direction. Bias averages the signed errors to show whether the forecast tends to overpredict or underpredict. Together, these metrics summarize how well the naive baseline forecast performs. We report two key error measures for the naive baseline forecast. The mean absolute error shows the typical size of the prediction errors, regardless of direction, while the average signed error shows forecast bias. If the signed error is positive, the baseline forecast was generally lower than the observed strain. Create one figure with two vertically stacked plots using Matplotlib's subplot tool. Share the x-axis so the date labels line up across both plots and use a large enough figure size for readability. This layout keeps the forecast and error views together in one clear visualization. Plot the observed strain data over time, then add the naive forecast to the same subplot so the actual and predicted values can be compared directly. Label the vertical axis as microstrain to make the measurement units clear. A legend is added to the first subplot in the upper left to distinguish the observed strain from the forecasted strain. The subplot is also given a title, identifying it as the bridge strain baseline forecast, making clear that the plot compares observed strain with a naive forecast. This section shows forecast errors with a bar chart, where each bar represents the error for a specific date. A zero reference line helps indicate whether the forecast was too high or too low compared with the observed values. The y-axis is labeled error, so the meaning of the bars is clear. Label the second subplot's horizontal axis as date to show that it represents time, and give the subplot the title Forecast Error Over Time. These labels make it clear that the chart shows how forecast errors change across dates, improving readability and interpretation. To make the plot easier to read, use Matplotlib's automatic date formatting to adjust the x-axis labels. Then apply a tight layout so the plot elements fit neatly, and display the figure to review the forecast and error data. This script creates simulated bridge strain data with a trend, weekly pattern, random noise, and two unusual spikes. It uses a simple persistence forecast, where each day is predicted from the previous day's observed strain. The script measures signed and absolute errors, including mean absolute error and average signed error, showing that the model often underpredicts when errors are positive. The resulting plots compare observed and forecasted strain and show how errors change over time, especially around unusual events. In this lecture, you learned to represent civil engineering time series data using pandas and NumPy structures, extract temporal features such as lag values, rolling averages, and rate of change, and evaluate simple time series baselines and visualize prediction errors. In the next module, Module 7, we will go over none.
Thank you for your attention. See you all in the next lecture.